In this lecture, we will learn about recursion. Up until this point, all of our solutions to coding problems have been solved using an iterative solution, using programming constructs like loops to iterate over data and solve a problem. Recursion, put simply, is when a function calls itself. It breaks down a large problem into a smaller subproblem that can be repeated over and over. In order to write recursive code, we need to have a base case, a case where when a condition is met, the function stops calling itself repeatedly. Otherwise, we will have an infinite loop, which will crash our program, as we learned in a past lecture. The recursive calls to a function should progress in such a way that each time a call is made, it comes closer to the base case. This lecture will take a look at one of the most commonly solved recursive problems in all of computer science, the Fibonacci sequence. The idea behind recursion is that we represent a problem in terms of one or more smaller problems, and add one or more base conditions that will stop the recursion once they are hit. If the base case is not hit, then we can actually get a Stack Overflow exception in our code. This is because each recursive call is stored on the stack. There is only so much memory on the stack, so if all of it is getting used up due to recursion that never stops, you may end up getting a Stack Overflow exception. It is important to note that every problem that can be solved iteratively can be solved recursively, and vice versa. Let's take a moment to compare and contrast recursion and iteration. Recall that iteration is when we use loops to iterate over data. Recursion is when we write a function that calls itself over and over to solve a problem. Recursion makes a program more readable. It is also more efficient than iteration, meaning that if we run a recursive program and an iterative program solving the same problem, the recursive program will always finish first. However, one drawback of a recursive solution is that it requires more space than iteration. The reason for this is that every recursive call has to be stored in memory. One advantage of recursion is that it makes a program more readable. The Fibonacci sequence is an algorithm that shows exponential growth over time. Each new term in the sequence is generated by adding the previous two terms. We start out with 0 and 1, and then build from there. Here are the first 12 terms of the Fibonacci sequence. Let's take a moment to understand exactly what is happening here. We start out with 0 and 1. Then those are added to make 1. The 1 and 1 are added to make 2. Then the 1 and 2 are added to make 3. Then the 2 and the 3 are added to make 5. Then the 3 and the 5 are added to make 8. In other words, each number is the sum of the two previous numbers. How can we use recursion to write a function that will take in a number n and find the nth Fibonacci number? To do this, we are going to need to write a function that calls itself and follows the rules of recursion. Remember what we need in order for a program to be a working recursive program. The function needs to call itself. Each call needs to progress it closer to the solution, and the base case needs to be hit, stopping the recursive calls. Okay, let's stub out a function here in Python. We will name our function fib. It will also take in a parameter that we will name n. Let's ask ourselves a few questions. What is the base case? And what is the subproblem that is happening in the main problem? What pattern do we see? First, the base case. Remember, a recursive function can have more than one base case. In this case, there are two base cases. If n is 0, then we return 0. If n is 1, then we return 1. These two numbers come at the start of the Fibonacci sequence, and once we hit them, we know that we have reached the end of the program. Let's add code handling the base case to the function. If n equals 0, or n equals 1, then we will return n. Now we need to address the other questions that I posed just now. What is the subproblem that is happening in the main problem? And what pattern do we see? I noticed that each number is the sum of the two prior numbers in the pattern. If we're saying that n is the nth term in the pattern, then we can say that each term is equal to n-1 plus n-2. In other words, that term is the sum of the number one space behind it and two spaces behind it. So we can add the following code to our program. Believe it or not, that is all of the code needed for the Fibonacci sequence program. To test our code, let's print out the result when we pass in 11. Since we consider that the 0th Fibonacci element is 0 and the first Fibonacci element is 1, The 11th element should evaluate to 89. One drawback of using recursion is that each recursive call is stored on the stack, taking up more memory. So, is it possible to write the Fibonacci sequence code in constant space, meaning that no matter the nth element passed in, the code uses the same exact amount of space to execute? Yes, if it is done using iteration instead of recursion. Remember, any solution that can be done using recursion can also be solved using iteration, and vice versa. So how would we go about writing the code we just wrote to get the nth Fibonacci number using iteration? Let's start out with a new method stub. The function will also return an int and take in an int n, and will be named fib2. If the n is 0 or 1, we want to return n. Then we need a few variables. We need to store the second to last number and the last number, as well as the current position we are on. We will have an int variable named slast, initialized to a value of 0, that will store the second to last number to the one we are currently on. The last number variable, meaning the number 1 behind the current number, will be initialized to 1. And the curpos variable will be initialized to 2. Then while the current pos is less than or equal to n, we will set the temp variable equal to the last variable equal to the last plus the slast variable, and then set slast to temp. Next we need to increment the current pos. Outside of the while loop we will return last. Okay, let's step back and look at what all of this means. While the current position we are on is less than or equal to the number passed into the function, we store the value of last, the number before the number we are currently on, inside of a temp variable. Then we set the last number equal to the last number, plus the number behind last, creating the next number in the Fibonacci sequence. After that we set slast to temp, so the second to last number becomes the last number from before, and then we move forward one position by incrementing the current pos variable. At the point when the current pos variable is greater than n, we can return the value of last, since it is the nth Fibonacci number. Let's test out our code by printing it to the console. As you can see, we have confirmed the code is working, since we passed n into our fib2 function, and 89 is the 11th number in the Fibonacci sequence. In the next lecture, we will look at a recap of what we learned in this section of the course.